Okay, so before we go and talk about directed set, let's just basically do some classification problem. Okay. So we've given relations here, and we want to see if they are reflexive, symmetric, transitive, and antisymmetric. So like A is 1, 2, 3, 4, and R6 is a relation again given by A cross A, such that R6 is given by 1, 1, 1, 2, 2, 1, 2, 2, 2, 3, 3, 2. The question, is it reflexive? So why not reflexive? No. Yeah, because this because 1, 1 is there, but 2, 2 is there, but 3, 3 is not there. Does not belongs to R6. Yeah, that's the justification. What about symmetric? Let's see. If 1, 2 is there, then 2, 1 is there. If 2, 3 is there, then 3, 2 is there, right? And rest everything works out. So it is indeed symmetric. Yeah. Again, why? Let me just write down why is that the case. If xy belongs to R, this is same as saying implies is in, so if xy belongs to R, then yx belongs to. Is it transitive? Let's say. Okay. So 1 is related to 2, and then 1 is related to 2, and 1 is related to 2. Sorry, 1 is related to 1 and 1 is related to 2. Therefore, 1 is related to 2. Okay. Now let's see. 2 is related to, so let's see. So 2 related to 3 and 3 related to 2. All right. So now, so it is symmetric. Why? Because we already checked that. Now transitive. 1, 2, then we see whenever there's 1 first, 2, then 1, 2 is there. Where else? Nowhere else, right? Now let's see. 2, 3, 3, 2, then 2, 2 is there, right? If I write it first, however, if I write 3, 2 and 2, 3, but 3, 3 is not there. So not transitive. Why? Because 3, 2, 2, 3 belong to R6, but 3, 3 does not belongs to R6. Yeah. So when you're given this finite example, you have to be very careful. You have to analyze each and every case. If you miss out on your case, then you might basically get into trouble. Because rest, in my opinion, rest everything is working out properly. These are the two which is really creating the problem. Okay. Now, what about antisymmetric? Is it antisymmetric? Let's see. What is the definition of antisymmetric? If 1, 2 is there and 2, 1 is there, then 1 must be equal to 2. That's not the case. Yeah. So this is not antisymmetric. Why? Because 1, 2 and 2, 1 belong to R6, but clearly 1 is not equal to 2. So this is not what? Not antisymmetric. Okay. Let's look at another example. R7, which is a subset of A cross A, x comma y such that x is less than equal to y. Yeah. Is this, so we have already checked this though, right? Have we not? Yeah. So clearly 1, 1, 1, 2, 2, 3, 3, 4, 4 is there. So this is reflexive. We also saw it's not symmetric, right? Why? Because 1, 2 belongs to R7. Let's just write down the reason here why. 1, 2 belongs to R7, but 2, 1 does not belongs to R7. Okay. Now, transitive. It is transitive. We already have checked this. Yeah. Already checked. Is it antisymmetric? And we have also checked that. That is true. So this guy is what? Is reflexive, antisymmetric, and antitransitive. Not antitransitive. Reflexive, antisymmetric, and transitive. So this is so-called partial order. Okay, makes sense, right? Now, question: can there be a relation which is everything, all 4 of them? And the answer is yes. Let's take set A to be 1, 2, 3, 4. Now, can you give me an example of a relation which is everything? Yeah, makes sense, right? So this guy is everything. So that is, so here we have something which is all, okay? So they are not an opposite concept, right? Yeah, so it could happen that it's everything at once. Now, let's count the number of reflexive relations. Let's count the number of symmetric relations. Let's count the number of transitive relations, and let's count the number of anti-symmetric relations. Okay, so this is interesting. So now, let R be a relation. So first of all, how many relations are there? So what is the definition of relation? It's a subset of A cross A, right? What is the only what is the only defining feature for relation? It's a subset of A cross A. Yeah. So how many relations will exist? As many as there are subsets of A cross A, isn't it? How many subsets are there for any set? There's exactly the size of the power set, isn't it? So let's see. So size of A cross A is n times n, n square. Of course, we should start with size of A, n, isn't it? The size of A cross A is n square, right? And now how many, what is the size of power set of A cross A? It's going to be 2 to the power n square. So therefore, the number of relations on A is 2 to the power n square. Does that make sense? All right. Now, next problem. How many of them are reflexive? So let's see. So let's take a set A. Let's work with something finite and it will give us an idea. Let's take 1, 2, 3. Now, what you want is that 1, 1, 2, 2, and 3, 3 must be there. There's no option for them. You see what I mean? Yeah. The more count comes when you have an option of including or not including something. Right? So if you take n square elements, so let's take a set of size n, there are n square element in it. Out of those, how many of us form 1, 1, 2, 2, 3, 3, 4, 4, 5, 5? N of these sets, right? Do you agree? And so we do n square minus n. Why? Because these n are not option. No, they have to be there, right? So we have those for sure. And for the remaining, we can have a power set argument. So we can have 2 to the power n square. Okay, let's try to write this properly again. Let me write down the idea behind it. So let's take set A to be 1, 2, 3, dot, dot, dot till n. Okay, yeah. Now, R is reflexive if what happens? If 1, 1 all the way and n belong to R, right? So now, how many elements remain now from the A cross A? So now we have option of including or not including A cross A minus 1, 1. Do you agree? Right? These are their mandatory. They cannot be not there. And out of that, so the size is going to be n square minus n size set. We have option of including or not including. So it's going to be what? 2 to the power n square minus n. Yeah. If you include or not include. So you're looking at all the subsets of what? The remaining, and then you look at the power set, and then you take the union, basically. So you can think about this as follows. So let's call this as set B. You're looking at power set of B, union 1, 1. This will be all possible relations. Yeah, does it make sense? So for this one, you have size 2 to the power n square minus n, and these are mandatory. They will be there every time. So therefore, the number of and number of what? Reflexive relation is 2 to the power n square minus. Is that okay? So let's see why reflexive, the number of reflexive set is, let's take an example, 1, 2, 3 to be my A. All right. Now, so reflexive relations basically is going to be 1, 1, 2, 2, 3, 3. These are already there. Now, so let me just write down what is A cross A first of all. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 3, 3, 2, 2, 3. That's right. Thank you. And then we have, let's just 3, 1. We have 3, 1, 3, 2, 3. Do you agree? Yeah. Now, what is my A cross A minus 1, 1, 2, 2, 3? That is going to be what set? That's going to be 1, 2, 1, 3, 3, 2, 1, 2, 3. And then we have 3, 1, 3, 1, 3, 3, 3, 2. Yeah. Now, so now for reflexive, any reflexive relation R, let's R be any reflexive relation. This will be again union any of these subsets of this, right? Do you agree? If I include, say, union 1, 2, then it will be still reflexive. Do you agree? Yeah. So I can do union with any set X where X belongs to what? Power set of this, whatever you want to call this. Let this be B. If I take union with power set of B, then I will get all possible relation which are what? Reflexive. Because 1, 1, 2, 2, 3, 3 is there. See, for example, I could include here 1, 1, 2, 2, 3, 3, and then we have what? Say any subset of this. Yeah, take any subset. Let's say it was size 1 subset is what? 3, 2. This will be still reflexive. Yeah, or any subset here. So how many subsets are there for P of B? So how many subsets are there for set B? That is equal to the power set of B, right? What is the size of this guy? This is 3 square minus 3. Yeah, so that's the idea pretty much. Okay, so if you are looking for reflexive set relation, number of reflexive relation, you remove n square n because n is not optional, it's compulsory. Out of that, so we have n square minus n element now from A cross A, and they can be included or they cannot be included. That's fine. So that is the reason why we have so many. Now, does that make sense? Okay. All right. So let's take a 15